Good afternoon, everyone. I'll start just by letting you know, if you didn't get my email from a few minutes ago, that I have updated these lectures and also the lecture notes. So I'd ask you to download the lecture notes PDF before the tutorial, because then we'll be following that in the tutorial. In any case, you can also follow through the slides, because in the second lecture I'll explain the exercises that we'll be doing. So now we're going to look at activations inside the network, and also for the output, and also what loss functions we can use in different types of problems. We're going to look today also in particular in regression problems, in binary classification problems, and in multi-class classification problems. So I'm going to start just with a brief overview of the pros and cons of having wide models like linear models, for example, versus deep models like deep learning models, deep neural networks like we've been using. And also talk about this problem that was a really big problem for deep learning until about 2014, 13, about there, before these rectified linear units. So this is the vanishing gradients problem when we use activations like sigmoid, for example. Then we're going to look at different activations, where to use them, how, and also different loss functions that we can use to optimize our models. So first, this question of using a wide model. For example, we could use a neural network with a single hidden layer, because it can be demonstrated that if we have some function that is not constant, bounded and continuous, for example, the sigmoid activation function, so it is bounded, it does not go to infinity, so it cannot be a linear function or something like that, but it's continuous and not constant, and so does some nonlinear transformation. Then if we have some region of some parameter space, without loss of generality, we can consider between 0 and 1 in all dimensions. So this would be an m-dimensional space for this m here. We can use a linear combination of these, the outputs of this function, this bounded continuous function, for example, the sigmoid function, to approximate any function that is continuous inside this region. So basically, what this means is that we can use a hidden layer. So this would be the hidden layer, a set of n neurons, all with these activations and with this linear transformation as the input. We could use this hidden layer with a sufficient number of neurons to arbitrarily approximate any continuous function inside some specific volume. So we cannot guarantee that we can approximate overall infinity, but in a bounded region, we can approximate it arbitrarily. So in theory, we could use one hidden layer to approximate any function to within practical requirements, because we can always scale what the region of interest is. And so we could theoretically use a single hidden layer to solve any machine learning problem like classification, regression, and so on. So the problem here is that we can theoretically do that with one hidden layer, but we don't know how many neurons we're going to need. And when we're dealing with problems of classification, for example, the power of the classifier is proportional to the ability to shatter the data sets. So basically, we need more oscillations to be able to shatter data sets better. I'm going to explain a bit more what that is. So those of you who took machine learning probably remember the Vapnik-Chevonenkis dimensions. But anyway, I'm going to review that. But the idea is that if we have stacks of neurons in layers, by chaining those nonlinear transformations, we can make more rapid oscillations of the values, and so cut in more different planes easily. So let's see this Vapnik-Cherenkov dimensions. We say that some hypothesis class, for example, the class of all linear classifiers in 2 dimensions, this would be one hypothesis class from which we can take lines and use them to classify our data. We say that some hypothesis class H shatters a set S if for any labeling of the set we can always find one hypothesis in the hypothesis class that classifies without errors, that is consistent with the set. For example, suppose we have a set of 3 points in a triangle like this. Then with any labeling that we put in the 2 classes, for example, this one red, these 2 blue, these 2 blue, this one red, and so on. There are 2 other cases here which is all red and all blue, but these are not very interesting because those are trivial to classify. But in all these cases, we can always find a line that allows us to classify the points without errors. So a linear classifier in 2 dimensions shatters 3 points. This is the VC dimension of the classifier. So the Vapnik-Cherenkov dimension is the maximum number of points in the set that can be shattered by our hypothesis class. So the more ability our model has to do these kinds of things, these kind of cuts, the greater the VC dimension. So what happens in practice is that although we can use a single hidden layer to approximate any function arbitrarily, if we stack hidden layers, we can get more oscillations and we can increase the Vapnik-Cherenkov dimensions without having a large number of neurons. So we can actually use fewer neurons if you have a deep model than we would need to do the equivalent task with a single hidden layer. And that helps because we need not as much data to train the model and so on. However, there is always this problem. I mentioned this in a few weeks ago, which is the no free lunch theorem, that in theory, if we have a learning algorithm that is good for one particular case, then there could be theoretically, there would be in theory a distribution of data for which our algorithm would perform worse than average. The intuition for this, you can think of a learning algorithm as trying to extrapolate from the data to outside the data. And to do that, we need to have some inductive bias. We need to have some bias about what things extrapolate from the data and what things don't extrapolate. For example, if we are using a linear classifier, we are biasing our model towards looking for linear frontiers, straight frontiers between our data, and using that to extrapolate. So if we have some data where this bias, this inductive bias works well, we could theoretically think of some different distribution of the data where this inductive bias would mislead us and lead us to get the wrong results more often than not. So basically, this is the no free lunch theorem. Any algorithm that is better than chance in some distributions of data will perform worse than chance in other distributions of data. However, in real life, data is not distributed in any theoretically possible way. So this is a mathematical result, not necessarily what happens in our universe. So basically, the best algorithm will depend on the problem, and some of them work generally better than others for the kind of data that we have in real life. This wouldn't apply in general for all mathematically possible data, but it applies to real data in real life. So here are basically 2 trade-offs between wide or shallow and wide models versus deep models. So with linear models, we can use we use just one layer, for example, one single nonlinear transformation, something like that, and they tend to be better at memorizing interactions between some features or some examples. For example, we can find that customers who purchase some specific item also purchased another type of item. And this works well if we have data on exactly the examples. However, one drawback of the linear models, even though they're easy to interpret and they give us, well, this kind of information, is that they are poor at generalizing what is similar. We know that people who saw that movie also saw that other movie, but we cannot easily use a linear model to say that people who like horror movies also like action movies, unless we humans put in those features specifically in the data, because the linear model cannot generalize into those kinds of combinations of features. Deep learning models are much better at generalizing those kinds of correlations, even without feature engineering. So we can find these kinds of correlations between types of movies and so on in the encodings the deep models find. However, they tend to be more black box, hard to interpret, and it's difficult to understand exactly which features they use. So this is an example of the kinds of images that mislead image recognition with deep learning, and we have here some cupcakes and poodle dogs, and you can see that some of the cupcakes look like the faces of the dogs. Here are some mops and some dogs. Here are other dogs with bagels. So even for our own neural networks, sometimes it's hard to tell them apart because we are looking at these kinds of generic features, and image classifier algorithms sometimes make these kinds of mistakes. And when this happens, it's hard to say exactly why the mistake is occurring. So even when we look at the image, we can see that sometimes it's a bit confusing whether it's a dog or something else, but we cannot really point to a single feature that is making us confused about those. So this is a problem with deep models, is that they are hard to understand and how to figure out which features they are actually using to perform the classification. So just to a brief look here, this is an interesting paper from 2016, in which they combined two models, a wide and shallow model, logistic regression, and a deep learning model for embedding. So this was to try to take advantage of the strengths and weaknesses of both of them. So the shallow model was best at memorizing co-occurrences that were examples that were correlated specifically in the data, like fried chicken correlated with chicken and waffles, where in what people used to eat and so on, but not things that could fall into the same kind of category. For example, fried chicken and hamburger. Whereas deep models tend to find those embeddings, those encodings inside the network that bring together vectors of representing different examples that show some other more subtle correlations. So they manage to group these generical categories. And so they tried this on the Google Play site, and on 1 million apps and with 1 billion active users. So they tested on just a small percentage of the customers at the time, but they managed to have some gains by combining the two models. They gained almost 4% on the number of purchases. This is a recommender model that when someone is looking at an app or buying an app, it recommends another one that the model thinks the person is likely to buy. And this kind of improvement in sales really translates to a lot of money. So this is an example where even though we'll be focusing on deep learning because of unstructured data and so on, I'd just like to point out that this is not really just a matter of using deep learning for everything. Sometimes we must bear in mind that there are trade-offs and there may be good alternatives. So wide models tend to be better at memorizing what occurs actually in the data. Deep models tend to be better at generalizing, at learning combinations of features from the data and finding new types of groups. However, this makes them much harder to interpret. So let's see another problem that occurs with deep models, which is this problem of the vanishing gradients when we are training the models. When we are training with backpropagation, we are chaining all these derivatives together by multiplying all the derivatives to compute the derivative of the loss function with respect to the weights that we are adjusting. However, this may be a problem if somewhere along the chain we find a derivative that is close to zero. Since these are all products, if something here is close to zero, then the whole chain will start to disappear. And when we have gradients that are close to zero, then we don't have information to update the weights, and training will start to slow down and eventually stop. So this happens with the sigmoid layers easily, because the sigmoid function saturates and the derivative tends to zero. So if you try this, you can play with TensorFlow Playground. You can select the sigmoid activation. You select here a data set. We put a few hidden neurons, and then we train. And with a single layer, this works well. And after 370 epochs, we have a good result here. If we go for a bit more complex problem, so this spiral, which has the blue ones here and the orange ones here, we cannot do this easily with just these 8 neurons in a single layer, but we can try to put more layers. However, even after nearly 1500 epochs, we still are not getting there, and things are not improving very much. So adding even more layers does not appear to help, maybe even makes it worse. This is after 2000 epochs, and we're still not getting anywhere. So the big problem here is that a sigmoid activation function has this kind of shape, and so if we start moving away from the center where the gradient is highest, we start getting into those extreme regions where the derivative saturates, or where the function saturates and the derivative is zero. So if we go onto this side or this side, the derivative starts approaching zero. And when this happens at some neuron in our network, then all those chain derivatives, all those products will start falling to zero, and the training slows down and stops. So even if we add more layers, we increase the power in theory of our model to classify these kinds of examples, but in practice we are also making it harder to learn, because now we are chaining more sigmoid activations, and eventually we drown all the derivatives, everything goes to zero, and the model doesn't learn anything. So this was a big problem until the rectified linear unit. This is a strange kind of activation. So sigmoid activation, we have this formula, we have this smooth curve from 0 to 1. We have similar other activations that were used. For example, the hyperbolic tangent went from -1 to 1, but also had the similar smooth curve. And this seemed to be the best way to go, because we have this smooth curve, the derivatives are continuous, and everything looks neat and organic. But then people tried this rectified linear unit, and this is basically if the input value along with the bias, so this x here is the linear output from the neuron before we apply the activation. If this is below 0, then we just output 0. If it's above 0, we output the same as the input. So it's two straight lines forming this elbow. And this is enough to give the nonlinear response that we need for our nonlinear transformations in the network, and has the big advantage that the derivative is constant on this side and also constant here. The derivative is discontinuous here exactly at 0, but that's usually not a problem. We can just assume that it's 0 all the way here, and then it's not 0, it's constant, equal to 1 on this side. So this helps with the vanishing gradients problem, because the gradients now do not vanish, at least for neurons that are active. If the neuron is firing, then the gradient is always 1 for that neuron. And this, if we use, for example, sigmoid activation with 3 layers, after nearly 1500 epochs, we still have not trained much, not learned much. But if we use rectified linear units, even after 300 epochs, we already have a good result here, because we are not suffering that problem of bogging down on training due to saturation, and we can speed up things. So the same, even if we add layers, it still works, and it works fast. So here 200 epochs, and we already have some good results. So if you want, you can try this with the TensorFlow playground. It's easy to choose the activations and to run the different simulations. So basically, the advantages here are that rectified linear units are very fast to compute because we just have that simple function and do not saturate for positive values. There is a slight problem that if the neuron is outputting the linear part is negative, then the output of the rectified linear unit activation is 0, and so the gradient is also 0. And in those cases, if the neuron is not firing, it's not learning. The weights will not change because the gradient is 0. So neurons can die if it happens that they are in a configuration that they always fire at 0 for all the examples in the training set, then the neuron will not recover. It will die permanently. There are some variants that fix this problem. So the standard rectified linear unit can die if the input for the activation is always negative. That is the net output of the linear part of the neuron. But if we add some small leak, like in the leaky rectified linear units, then it's still a non-linear response because the gradients are different. But since we don't have a 0 gradient on this side, we can actually recover if the neuron falls on that side, and if it's necessary, and so it will learn the right parameters regardless of where it lies here. So this is the way it's sometimes shown in the literature, where we have this alpha parameter here that provides this inclination. In TensorFlow, it's actually a multiplication, and the default is 0.2, but you can change it if you use leaky rectified linear unit. Then there is a parametric rectified linear unit, which is similar to leaky, but this is actually an additional parameter that the neuron learns. So it's affected during training and it's optimized. We have randomized leaky ReLUs in which the alpha here is drawn from a uniform distribution, where we give the limits, the lower and upper bounds, and then after the network finishes training, all the neurons are set to the midpoint, the average of this distribution. So during training we have some randomness. We're going to see these kind of things with regularization later on. Not today, but in a few weeks. So comparing different data sets, this paper from 2015 showed that leaky rectified linear units appear to be the best. There are also some other variants like concatenated rectified linear units. So basically we join together one ReLU for one side and then the inverse for the other, and we get this V. This exponential linear unit uses the linear part in the positive here, but then adds this exponential part here behind. So the derivative is always continuous too. This is a bit more expensive to compute, but has some nice properties in some cases. So, but these tend to be more specific examples that are used in some particular cases. But you can always experiment. If you have a specific problem, you can experiment which work better. So basically, this is the idea for the activations that we generally use inside the network, so in hidden layers. When we are dealing with hidden layers, we must take some care in deep models about not bogging down training by just vanishing the derivatives to 0. So usually in the hidden layer activations, we will use rectified linear units or some variants like leaky rectified linear units, for example. These is generally the recommended choice for the hidden layers. There are some exceptions. For example, in some recurrent networks like long short-term memory recurrent networks, where they already have the nodes have very specific activation types, so these are more fixed and we cannot just change the activations. But for the kind of things that we're going to look at in this first half of the semester, this should be the general approach. In hidden layers, use rectified linear units. Some variants you can try, but if you try to use sigmoid activation and so on, you'll probably have problems training your models. For the output activations, it's different, because now the output layers are not merely stacking on nonlinear transformations. The output layers are giving us what we want from the model. So in this case, we really need to think about what is the kind of problem that we are trying to solve. And so as a function of that, we need to think about the kind of activation that we want. So what output we want from our model. And here we have different choices depending on the kind of problems. So if we are doing regression, we are trying to make our network output some continuous value that is as close as possible to the targets that we have in the training set. So generally, we do not want to restrict the output of the network to a specific range, for example, like would happen with sigmoid activation, or with the rectified linear unit, where the output could only be above 0, something like that. So usually when we are doing regressions, the last layer of the network, which can be for a univariate regression problem where we're trying to predict, if we in the regression problem we're trying to predict a single value, then the output will be just a single neuron with a linear activation. That is, we do not add any activation function, we just use the linear part of the neuron. For binary classification, the sigmoid activation is a good choice, like what happens in logistic regression, because with an output value between 0 and 1, we can interpret it as the probability of belonging to class 1. So if we only have two classes and we are distinguishing between class 1 and class 0, for example, we can use the value of the sigmoid as representing the probability of belonging to that class, and this gives us a nice way to interpret the results of the network. Sigmoid activation is also good for multi-label classification. Multi-label classification is a case where we are trying to predict several different labels, but each example can have several of them at the same time. So, for example, we want to predict what kind of appliances there are in some apartment, and they can have TVs and oven and microwaves and so on, and each house can have combinations of those. So for each one of those, we could use one output neuron with a sigmoid activation that would give us the probability of there being that particular appliance in the house, and it would not be mutually exclusive, because houses can have several different appliances. For multi-class classification, we can use softmax. Softmax is a generalization of the logistic function, and basically what it gives us is a vector. So this vector is composed of a number of neurons, k neurons, which correspond to the k different classes. Now, in multi-class classification, it's different from multi-label classification, because in multi-class, each example can only belong to one class, so they are mutually exclusive. For example, we are trying to predict the brand of a car or something like that, and it can only have one of those, so they are mutually exclusive. And the advantage of this softmax function is that it gives us a vector in which all the elements are between 0 and 1, and the sum of the elements is always 1. So we can interpret this as a probability distribution. For example, we have 10 classes. We're going to see an example here in hand-digit identification in the second part and in the tutorial. And there are 10 different digits, and each digit that is presented to the network will belong to only one of the 10 different classes. So by using softmax, we will have the sum of the probabilities of belonging to each of the different classes will always be 1. And each of those values will fall between 0 and 1. So we can interpret that as the set of probabilities of belonging to each of the classes. So these are the different activations that we can use, some examples for different kinds of problems. Okay, so now let's look at the loss functions that we can use. first, let's see the general idea here, that we have a set of labeled data, and if we are doing classifications, we'll start with this simple example first. If we are doing regression, for example, supervised learning, we want to predict some epsilon value from the features, the x, and in the case of linear regression, our model is just a linear combination. So let's go to the simplest example here, where we have only one input value, and we are going to predict the output value with a straight line. So we need two parameters to specify the line, and this is what gives us our prediction. So we have here a set of data, for example, and many different lines that we could draw, and the question is, how do we decide which line is best? So let's assume something about the data, and this is what happens when we need to generalize from the sample that we have to the rest of the universe. We need to assume something that will allow us to extrapolate. So let's assume that the y value is some function of x plus a random error. This error is normally distributed with a mean 0 and some variance here. And we can approximate f. What we want to do is we have our model, our straight line, which depends on parameters, and we're going to use that to approximate this unknown f function that relates x to y. So given that we have this distribution of points, this data set, and this is just a theoretical consideration here, the joint probability of the x and y's are equal to the product of the marginal probability distribution of those different x values and the probability of the y values depending on each x that we have. So we can compute the probability for our whole data set by just multiplying the probabilities for the individual points. So now if we can have the probability, the distribution of this x and y, and if we can compute that, the probability of x and y from our function, this is the likelihood of the parameters in our function. So basically our function is telling us where y should be as a function of x and how probable it is to find y in some particular place. For example, if we have this line here, and if we assume a random error around the line for the y value, then we could compute the probability of the y falling here, or falling here, or falling here, and so on. So we could use our function to compute the probability of the data as we see it. And the probability of the data given our function is what we call the likelihood of the function. So this because we cannot really talk about the probability of our function, of our parameters, because they are not random variables, but we can assume the data to be a random variable. We draw data at random, and so there is some probability of the x and y's coming with that particular combination. So what we want to do here is to maximize the likelihood of our function. That is to say, find the parameters for which the data is the most probable that we can make it. So we can just start by doing some transformations here. So the likelihood is this product of these probabilities of the data. We can take the logarithm to avoid having to do all these products. So if we take the logarithm, eventually these come out as sums. Now we can replace also the normal distribution, because the probability of y as a function of x, we assume is y is determined by some function plus a random error, which has a normal distribution. So we can apply that here. And we also can ignore the marginal probability of x, because it will not make any difference for our parameters, since our parameters are just about the relation between x and y. But this is a case for specifically because we're trying to predict y based on x. If our model was different, then maybe we could not get rid of the marginal probabilities of x. So this is what we get for the maximum likelihood of linear regression. Applying the logarithms, we can simplify everything to this. So basically, if we find the maximum of this expression, we find the parameters for that best fit our model to the data. That is to say, that make the data most probable, assuming that our model is correct. So, and if you see maximizing this has a negative sign here, so it turns out to be the same as minimizing the quadratic error. So this is where the squared error loss function comes in, is when we're doing regression like this, then minimizing the squared error corresponds to optimizing the likelihood, maximizing the likelihood of our parameters. And this is basically what you should do if you're doing regression. Then it's a good idea to use the quadratic error, the squared error loss function. So once we have the loss function, now we can do gradient descent like we saw before and try to find the minimum, computing the derivatives and all of that. So basically the trick here to train our model is to find what is the loss function that we're going to use and the one that really makes sense based on our model. So this will be a bit dry, this theoretical part, but the idea is not for you to memorize the equations, but just to get a notion of the reasoning behind this maximum likelihood. So suppose for the general case, we are not saying here whether we want to predict something or cluster or whatever we want to do, but in the general case, we have a set of examples that were drawn from some universe, from some population, and they were drawn with some probability distribution. And we can actually look at those examples. So these are the examples that we have. And also we have some model that we're training that it depends on some parameters. And depending on the parameters will give us some probability distributions for the data. So basically the model is a family of probability distributions for the data. If you imagine the line example, if the line is higher, then it tells us that examples are more probable in those higher regions. If the line is lower, it tells us they are more probable in the lower regions, and so on. So basically, adjusting our model changes the probability distribution that our model is telling us about the data. So the maximum likelihood estimator for our parameters is the set of values in our parameters that maximizes the probability of X of the data that we actually have. So we can change the parameters to make the data as probable as we can, and that is the idea of maximizing the likelihood. But we can also see this in a different way. First of all, one trick that we generally have to use is that it's very risky to do all these products numerically. So we apply the logarithm because the maximum of this product here, it will be the same as the maximum of the logarithm. And so we can just sum all the logarithms of the probabilities. So this is generally what we do. We maximize not the likelihood itself, but the logarithm of the likelihood. But other than that, it's just the same thing. Another thing that we can do is the set of parameters that maximizes the sum of all these probabilities will be the same as the set of parameters that maximizes the average of the probabilities, because this just means that we are dividing by m, but it's a constant, so it doesn't make a difference for the parameters that we'll find. So basically, this would be what we want to do. We want to maximize the expected probability of some x according to our model. So our model, we give an example and the model can tell us how probable that example is. And we want to maximize the average of these probabilities for examples drawn with some particular distribution, because these are the actual examples that we have. And intuitively, we can see that what this turns out to be is we want our model to give us a probability distribution that is as close as possible to the probability distribution we are getting from the data. So when we draw examples from the universe, this probability distribution should be what our model is telling us, because basically that's what we want our model to capture and to generalize. And we can see that this is indeed the case. This Kullback-Leibler divergence is a measure of the divergence between two probability distributions, and it's measured by the expectation, the expected value of the difference between the log probabilities, like this. So if we use this to compare the probabilities that our model is telling us to what we actually have in the data, the distribution that we have in the data, since the data is not dependent on the parameters of our models, then basically minimizing this divergence corresponds to maximizing this part here. So it's the same thing. The maximum likelihood expression turns out to be trying to fit the data on fit the probabilities our model is giving us to what the distribution is on the data. So this is a bit abstract at this level, but I just wanted to give you an idea that there is a common thread here. Even though we're going to find different loss functions for different occasions, the basic notion is the same. We are always minimizing the cross entropy between the probability distributions our model is telling us and the probability distributions we find in the data. That is always what we're trying to do when we are maximizing likelihood. But the thing is that now, depending on what the actual model is and what we are assuming, we can get slightly different or very different expressions by applying the same principle. So in supervised learning, when we want to predict some label, we can, for example, in linear regression, we can end up, when we maximize the likelihood or we minimize the cross entropy between our model and the data, we end up with the minimization of the squared error. If we use a sigmoid activation function to predict the probability in binary classification, then we have this logistic loss function. By applying exactly the same principle, we have this logistic loss function that we're trying to minimize, where the expression here, the g function, is the sigmoid. If we have multi-class classification, then exactly the same principle, applying the same principle, but now with a different activation function, which is softmax, we get this softmax cross entropy loss function. So the basic message here, for this course, you're not going to need to know the actual equations, so I'm just putting them here for information, but you don't need to memorize this. The important thing is to understand that we are always trying to do the same thing, match the probability distribution output from our model to the actual distribution of the data. However, with different problems that we're trying to solve, we need different outputs from our model, and these different outputs will result in different loss functions. So the take-home message is pay attention to what kind of problem you're solving to determine what activation you need on your network, and then depending on the activation, look at what loss functions are appropriate for your model and for the particular problem. Okay. So to sum up this part, we saw trade-offs between wide and shallow models versus deep models. One problem with deep models, aside from interpretability, I don't know if we are going to have time during the semester for this, but I'm going to try to fit in something about interpretability in a couple of weeks. But that is one of the problems. With deep models, it's harder to understand what's happening inside the model. Another problem that used to plague deep learning until a few years ago was this vanishing gradients problem, but this was a consequence of using those activation functions that saturate easily. So with rectified linear units and other approaches, there are lots of different methods that ended up being used, but this is mostly solved. So in general, you don't have problems with vanishing gradients anymore, as long as you choose the hidden layer activations with care. The output layer activations, those are determined by the kind of problems that we want to solve, and which in turn also determine what kind of loss functions are appropriate. So you can look up chapters 5 and 6 of deep learning. These go into a lot more detail than I go here, but it's a good source for getting a bit more grounded on this part. We're going to see some examples of activation functions in practice, so you can experiment in the tutorial, but you have here in this in the TensorFlow documentation, you have a list of the activation functions available and what kinds of parameters they take. So that's it for now. We're going to take a break and we continue at 10 minutes past 5.